solenoid symmetry, you could easily calculate the H field with really doing only minor integrals. Follow me on this? Now, did you look at any of the problems? Didn't do them? All right, was there any trouble at all? Nothing? Okay. I mean, because some of that stuff's kind of confusing. What we had was the integral form of Ampere's law. Is the integral of H dot dl around a closed loop is equal to really the I penetrating that loop. Enclosed or penetrating. And this is called the integral form of Ampere's law. The point form is really curl of H is equal to J. Now contrast that with Gauss's law. It's the integral of D dot ds over the surface, closed surface, is really here, that's equal to the charge enclosed. Very similar. And divergence of D is equal to rho V. Here, instead of a divergence, we have a curl of H is equal to J. And the integral of H dot dl, instead of a surface integral, is the I enclosed. Just remember, I'm trying to contrast Gauss to Ampere's law, the two things, so keep that in mind. Now the curl equation can be done in either spherical, cylindrical, or Cartesian coordinates. The one you have to know, the others I'll give you, but the one you have to know is in Cartesian. And that's AX, AY, AZ, DDX, DDY, DDZ, of HX, HY, and HZ. So that's a determinant. You all remember determinants back in the day? And the way I do them, I always take first AX. I'm going to say this is equal to AX. And then I go from, this is going to be a slanted diagonal going from the from the top left to the lower right corner in this way. So it's DDY working on HY positive. HZ, and it's minus D, DZ, HY. Now I know this term because whatever, if this is HZ here, or the Z component of the vector, and you're taking the derivative with respect to Y, the next term will always be the Y component of the vector with the derivative of Z, all right? It's always going to be opposite. Then it's going to be plus AY here, and with AY, it's going to be DDZ, and then I'm going to hit HX. Normally, you repeat this row and this row here. So it's DDZ operating on HX minus DHZ dx, and then plus for AY, AZ, pardon me, AZ, when you look at that, so AZ, if you come down the diagonal, will hit DDX of HY minus D dy of HX. And that's the form. Something I'll tell you about this. If you actually look at the order of this, just for a second, this is AX, it goes to Z, Y. If you think about that, that's like the positive order of crossing, right? If you go X, Y, and then Z. Here, Y, well, that, I'm going to tell you, it works for that one, it's not going to work for this one. Y, X, Z is opposite, and then this one is opposite as well. Well, anyway, that's the curl of H. And so, in the book, he has a couple of problems that require the curl operation. If you don't mind, I'll just grab my book. Chapter 4. I think I gave you a curl problem.
4.24.
Yeah, hey, can you read this one to me?
A, B, S, C.
Give me A.
which set of coordinates, like Cartesian?
Give me that, the Cartesian ones.
A is equal to 3xy squared over z in the ax direction.
All right, now, the only thing I'm doing here is sort of bookkeeping, just going through and making sure I do the derivatives properly. Once I state that, the rest is, it's over. If I've done that, and I know how to take a derivative. Strangely enough, you're gonna see a lot of engineers get bored doing this, and they're not attentive, and they'll make mistakes. I promise you they do. So if I take a look at this, first I have to take, this is only the x component, all right? So the minute I know it's only the x component, you can think of this instead of this a, think of it as h, it's the vector. And just say this is a vector h. The symbol doesn't matter. That way we can look here and know exactly what we're doing. If we take a look at this, it's only got an x component, correct? Now, if you look at this, that's a z and a y component. It means that one goes away. All right? This has got an x component. This is the z component. That goes away. Here, that's an x component. It's got a minus up in front. So those are the two terms we have to worry about. I do one of these just to make sure everybody understands the process. Now, when I take a look at this, the curl of this vector would be equal to the derivative of hx with respect to z. And in that case, what is it going to be? What's the derivative of that with respect to z? What's the derivative of 1 over z? Minus 1 over z squared, right? Right? I promise you that people make mistakes just like that on tests. So it's minus 3xy squared over z squared. And the vector direction is ay. Do you agree with that? Right? What's the next term? Well, there's a minus sign right off the bat, and it's az. What's the derivative of this with respect to y? It's as easy as it looks. It's just going to bring the 2 out, right? So it's going to be 6xy over z, right? And that's the answer. That's also equal to js. So if you were asked in a problem, find the current density at a certain set of coordinates, given the h field, you'd have to take the curl of the h field and simply evaluate it there. That's the basic process. Now for cylindrical and spherical coordinates for the operations, they're given in the back. They're a little more complicated. Where's the curl? Right there. If you look down there, and I want to make one comment. I'm not sure if in this edition it's corrected, but in the edition I had before, the curl and spherical coordinates was not correct. That looks right, but I'm going to check on it. I'll give you the actual curl and spherical coordinates. I think I did post that. Even in the one I posted, there's a row in the last term of the curl operation, and it should be an R. And that was, I think, in his book. Just remember that the curl is always going to, I mean, in spherical coordinates, will have R, not rho. All right, so that's that. Now, for the B field, I'm going to just tell you, you know how when we were in, we used, in the electrostatic equations, we had these coupling factors. We had D was equal to epsilon E, and J was equal to sigma E. Those are just the constants that relate to vectors. D is related to E by epsilon, and J is related to E by sigma. Those are simply coupling things. For the magnetic field, we have B, that's the magnetic field intensity, is equal to mu times H. Now, B is in Webers per meter squared. So B has the units of Webers per meter squared, or Tesla. And the symbol for Tesla is just that. And H, do you remember the units of H, class? H are amps per meter. Amps per meter. Contrast that to the units of E. What are the units of E?
Volts per meter.
Right. Now, what about D? Do you remember the units for D? coulombs per meter squared, right? The units of B are Webers per meter squared. So it's a dense, or it's really it is a density, it's a surface density, right? But there's similarities in all these things. H and E are very similar. If you think about it's amps per meter, volts per meter. This you can think of in a lot of ways as a current. This you can think of as a voltage. I mean, it is per meter, but believe it or not, there's a lot of similarities that you'll see in the problems we do with these. You're going to see later that the ratio of E to H, or I'm sorry, yeah, of E to H is something it's a constant in the atmosphere for any propagating wave, and it's called the intrinsic impedance. And you would think there would be an impedance related. If we have volts over amps, V over I, that's R, or in ohms, right? Impedance. I'll get to that later, but I wanted to mention this. Now, there's something else I'm going to tell you. For the B field, the divergence of B is 0. Now contrast that to the divergence of D. That was equal to rho V, right? This is important, what I'm about to tell you. This is more of a concept that gives you some insight into the physics. If I take the divergence of D, I get the charge density, right? It could be positive or negative, but it's the charge density. Here, I get 0. What that implies is there are no magnetic monopoles. You can't get a bunch of positive magnetic charge. They always occur in a differential form that's called a magnetic dipole. There's always a plus and a minus portion of any kind of magnetic moment, dipole moment. And there's never just a singular piece of magnetic charge. Now I say that's true at even the very small levels of 10 to the minus 8, 10 to the minus 9th meters, but in this modern era with the super colliders they have in Europe, the CERN facilities, they have busted apart things and seen magnetic monopoles. So I just want you to know that they exist for like picoseconds, but they can smash things up, and the aftermath does break apart these things. The thing about it is they're tightly bonded. It's almost impossible, and the distance of separation is so small that there's really no effective way to talk about anything but there's 0 magnetic charge. All right, just be aware of that, because we do later on, if you follow through and get into advanced electromagnetics, they do create a fictitious magnetic charge to solve problems. It's an equivalence thing, all right? I'm just going to tell you there's some things coming up that will, if you're not paying attention, you'll think that there is a magnetic charge. There's no such thing as magnetic charge in the magnet. It doesn't exist. It's always in a dipole configuration, and that's important. And his B field problems in his book are trivial. He'll say, if this is the H field, what's the B field? Multiply by U. It's a no-brainer. And the other thing I'm going to tell you about that, because the integral of B over any closed surface is 0, if mu is the divergence of B is 0, right here, this also implies that the integral of B dot ds over any closed surface is 0. That's absolutely true. Over any closed surface. And that's important. Now we know the integral of the integral of D dot ds over any closed surface is the charge enclosed. Well, if there's no magnetic charge, there's no magnetic charge enclosed. So keep that in mind too. These things will become more important later. Right now, it's just sort of an introduction. Now, in the book, then after this, the thing that they do is they talk about magnetic forces. In physics, did you have magnetic forces? Do you remember those? Yes? No?
Yeah.
All right, well, magnetic forces are real important to understand as electrical engineers, because electric motors are based on those, railguns are based on those, any kind of solenoid activity is based on those. And you know that there are permanent magnets that you can buy, and there's also electromagnetics where you can create a magnet, all right, by passing current. So how does it actually work? And we'll get to that, but now I'm going to talk about magnetic forces. This is something that's very, very interesting to me. And I'll talk about a little thing called a coil gun that a kid built for his master's project over in I think it was industrial. No, wait a second. It was it was a long time ago, textile engineering. Now they're part of mechanical engineering. But do you know what a coil gun is, anybody? You should look it up on YouTube. Just a whole bunch of coils of wire around PVC or something like that, small little thing. And then you literally just take a battery, short it across there, and if you put something like a nail in there, it'll go flying out, and it's absolutely silent. It is an unbelievably quiet thing. When I first saw that thing fire, it blew me away. I thought, this is an assassin's weapon. You don't hear it at all. And I'll show you this. We might even have some fun and build one here. Anyway, with magnetic forces, first thing, just for kicks, I'll show you a nail fly. When you talk about magnetic forces, this is something you have to understand. If I have a magnetic field B, let's say it's created in some way, shape, or form that I'll get to. You know current creates an H field, could create a B field, right? It's out there. If I have a charged particle Q in the magnetic field and it's not moving, there's no force on it at all. But if the charge takes on a velocity V, then there will be a force here. And the force will be perpendicular to both the B field and V. There will be a force, F, magnetic force, and that's equal to QV cross B. And this is real important. That force is in newtons. Contrast that to the electric force. If you just have a charge Q in an electric field, motion really doesn't matter. The force on this one will be in this direction, and the force is simply Q times E. Well, here, it is related to a product of the charge times the actual B field intensity, but it requires velocity. So things have to be moving. Now, here's something else that's interesting about this. When you take a look at this QV cross B, let me just show you it over here. Let's assume that the B field everywhere is up and a constant. So if I have a charge Q in this B field right here, and it's moving with velocity V, and this is charge Q. Unfortunately, I think I better restructure this. Let me do this. Let me say that I have V moving into the board. So I'm going to have a velocity going into the board. It's still going to have charge Q though, all right? I want to do it so I can actually sketch the path it takes. This is called a magnetic bottling effect. So if I have a charge moving at a velocity V into the board, I have V, right, cross B. Can you all imagine that? You take your right hand, this is the way they usually teach you. Take your right hand, put your index finger in the direction of V, and then cross it into B. So if you take this and go V cross B, the force is in this direction. QV cross B, force. You all see that? Now, what is that force doing? Well, the thing's moving this way, right? But it's being deflected that way. So in fact, what you're going to get is, if you're looking down from the top, you're going to get this. If you're looking down in the direction of the B field, you're going to get this thing being deflected. There's a force this way. The velocity is this way. So it's going to be deflected this way. And a little bit later, it'll have a velocity in this direction. Let me do this direction. And then what happens is, since the B field is actually in the direction of the board, when I do V, QV cross into B, actually I'm doing this the wrong way. Let me try to do this. I need, let me get a velocity out of the board. Try it this way. If this is Q and this is V coming out of the board, then QV cross B will be a force this way. And since it's going into the board, that way it's going to start bending, and it's not going to do it either. I'm going to have to do this a little different. Let's put the B field into the board. I'm not good sketching three-dimensional drawings. I'm trying to keep this 2D. So if the B field's into the board, like this, and then if I have a velocity, I have a charge Q, velocity V. If you look at this, then QV cross B would be a force in this direction. It would be up, straight up. Follow me? I'm just trying to make this point. Now, what that force is going to do is deflect this upwards, so it's going to start moving, and now the path would be like here. Then the velocity would be this way. If I take V cross B, there would be another force. It would be perpendicular to that in this direction. And it would keep deflecting it around in a circle until it came back to the same point. If there's nothing else, no frictional force. Do you follow me on that? Now this is the principle of any type of, really, in chemistry they have mass spectrometers, and they have things that deflect charges based on the ratio of charge to mass. So I'm going to go through this little thing with you. Now, if I look at this, I know that the actual force magnitude is simply Q times magnitude of V times magnitude of B. And I know the force is always perpendicular to the path that it takes. Follow me on this? No. So I'm going to make a bigger circle here. And again, the B field's in the direction of the board. And it's constant. And I have my charge Q. And it's being deflected around this way, in this direction. This is the path. So the actual force, the perpendicular force right here, magnetic force magnitude, is simply going to be Q times magnitude of V times magnitude of B. That's the force pushing in. Now you remember in physics, this thing will just circulate this way. In physics, you also learned that when you had anything in orbit, like a planet in orbit around the sun, there was an acceleration, if it was a circular orbit, V squared over R. Do you remember that? So now there's another force on this. And if this thing has charge Q and mass M, there's a force this way that's actually going to be due to the acceleration, and that force is on the mass, and that force, we'll call it mass force, is equal to the mass of the particle times V squared over R. And here, R is going to be, if that's the center point in this orbit, if this is R here, that would be mass V squared over R would be the force outward, right? And the force inward is QVB. Y'all remember this when you did it in physics class? Remember this stuff? So we equate those two because that literally is the condition. So that thing will just move this way. It will not in any way, shape, or form increase or decrease the radius. This force has to be equal to that force, if you follow me on that, or the radius would change. So when we equate them, we have Q times V, magnitude of V, times B, magnitude of B, is equal to mass. Now remember, that's the velocity. Mass times velocity squared over the actual radius of the orbit. I'm equating the two forces. And when I do that, I can see that the V, one V cancels on either side. All right? And now what I can do is find the radius, and I can see that the radius is equal to the mass times the velocity over Q times the magnitude of the B field. And that gives you the radius. So what happens when they're doing mass spectroscopy? Have you heard of mass spectrography or spectrography, right? When you did that, where did you hear about it? Where was it used? Do you remember? When they're trying to figure out a certain percentage of a molecule in a gas or any type of a gaseous thing, they can use a mass spec to figure out what percentage of that gas is any type of charge to mass ratio, which would tell them what kind of, the charge to mass ratio tells them what element's there. Now they do what they actually do with a mass spec is this. They have a magnetic field, a strong magnetic field, by the way. And they know the ratios. They ionize the gas, and they know the ratios of charge to mass. And if you look at this, or I should say mass to charge, they know this ratio. They know the velocity of the incoming particles because they're going to have filters that stop anything but this velocity between this certain stream. And they do it in a very interesting way. And they have a magnitude of a B field. So what they're going to do is throw in particles at velocity V. And the way they get that velocity, they accelerate it through an electric field. And they can easily calculate the incoming velocity of the particles and get them all to the same velocity. And when they come in here, then they're going to start deflecting. And if it's into the board and these are positive charges here, it's V cross B, and they'll start deflecting. And they'll deflect, and some will deflect up that way, some this way, some here, less deflection, more deflection, and they'll have slits cut here. And then they'll have detectors at those plates. And every time they're hit by one of these things, a small voltage pulse will happen. And this is kind of interesting the way a mass spec works. It's in a very, very low pressure environment so that there's no collisions through a region. The mean free path is much greater than the length that these things travel, as far as I understand. So they'll ionize particles, they accelerate them through an electric field, then they put a velocity filter on them because they have to be moving at the same velocity. Then they start looking at the charge to mass ratio, and they can identify very easily anything that's in there, from ionized oxygen to ionized helium, that's a tough one to ionize, ionized really any kind of gas at all, argon, things like that. And they do this, but that's the basis of a mass spec, and it's a very accurate instrument. It's also a very expensive instrument, from what I know. And they use that a lot. Gas chromatography, any type of gas phase physics uses that. The next thing, just remember that radius becomes essential, that you understand and how it's depicted. Now, after that, I'm going to tell you about one other phenomenon. Now, you understand that one other thing about this particle cannot gain energy from a magnetic field. Did you notice that? The only thing that's happening is the velocity is being changed around a circular orbit. So it doesn't gain or lose energy. It can if there's a gradient of magnetic field, and I'll show you that later. But it doesn't, in this case, really increase or decrease the energy. Now, it's the stronger the magnetic field, the tighter the orbit, the smaller the radius. And as the magnetic field lessens, it gets bigger and bigger. Now I want to just tell you about something that happens in our Earth's atmosphere. If you have the Earth like this, it has literally a molten core that you can think of as a magnet, north-south pole. And the field lines do something like this. This is a magnetic field line. Think of the electric field lines. They're really just trajectories for the electric fields. The electric field isn't a constant value there, but this shows the direction that the electric field has all the way around it, the way it's pointing. Now, if that's the magnetic field B, when charged particles are hitting our planet anywhere, think about it here. If they're coming in about the equator like this, I've got QV this way, and I've got my B field this way. So which way is it going to deflect? Well, QV crossed in a B would be into the board, right? But what happens is they get a big circular orbit like this. Imagine that into the board. I'm trying to show you something that's winding like this. But the more intense the magnetic fields get, the orbits start getting smaller and smaller. Remember, it has forward momentum because of the mass. Tighter and tighter and tighter. And they do it down here. If it's negative charge, it'll come in and gets tighter and tighter and tighter. Now, as that thing is accelerating, anytime there's an accelerated charge, there's radiation. Photons are being radiated. The only way you get electromagnetic energy that propagates through space is you have to accelerate charge. So as this is, remember that's electromagnetic energy. As it's coming down, the orbit's getting tighter and tighter and tighter, the acceleration. You get a higher and higher frequency, I mean the speed that it's rotating, you'd say the RPMs, is going up. And if you listen, anybody here ever use a ham radio? Well, if you have a proper equipment, you hear something they call whistlers. And have you heard this or not?
Like just
You know what it is?
background static or?
No. You can literally hear this if you know how to do it. You'll hear, if there's any kind of a solar storm or anything like it, you'll hear, and that's literally, it's the charge, it's bunches of particles, charged particles coming in, and they start at they start out here somewhere, and they're coming in, and their orbits get tighter and tighter, and you can literally hear them. It's a very interesting thing because that's literally caused by charged particles and what's termed a magnetic bottle. Now this is something else I'm going to tell you. It's not part of the curriculum, but it's kind of interesting. I did plasma physics in my master's work, and I was doing a lot of plasma stuff. And there's some odd effects that happen when you get extremely high density currents for any finite duration of milliseconds. There's all sorts of weird things that happen. One of them is called the Bennett pinch, but it's caused by something called a magnetic bottle. I want you to think about this. Suppose, for instance, we have a B field going into the board here, straight in, this way. But the B field has this type of a signature, the magnitude. So the maximum B field is here, and this can be distance Z. And the B field's oriented in the direction into the board, all right? Now, if I have particles coming this way, I have V cross B, right? And their spin would be upwards. But what happens is this. Actually, I've got this drawn. This is the magnetic bottle. Let me do this. It does this. And this is the B field. By the way, this can be several orders of magnitude difference, maybe 5 orders of magnitude difference. I'm just trying to give you an idea. Here, the particles coming in here would have an extremely small orbit. They would be very tightly bound because that B field's so strong. As they come here, the orbits would be much larger. And then they get smaller and smaller and smaller. Now what happens is, as those orbits start shrinking, it causes also a force in this direction. You follow me on that? As the orbits shrink, there's more force to resist it. And what this effectively does is trap all that charge in there if it's not a collision-dominated phenomena. All the charge will be between this point and this point. And think of like, if you had a funnel, take a marble and spin it on the outside. As it loses energy, it gets to the inner part, right? I mean, it gets closer and closer to the actual point it would just drop out if you had a funnel, right? But if the energy of that thing's not changing, I mean, if it's not losing energy, then it will stay at a certain altitude orbit. Do you all follow me on this one with a funnel? Well, magnetic bottles, what they have is the slope is extreme. You can think of the magnetic slope on this is super extreme. It's 3 or 4, it's actually 5 or 6 orders of magnitude. And they can confine charge in there. Now, the reason that's important is if you can do that with hydrogen, then you can fuse it into helium with enough laser energy and stuff like this. And do you know what the tokamak is? Have you heard of that? Well, they've been working on it forever, but they're trying to get literally the sun fusion here on Earth, but it's not low temperature, it's high temperature fusion. The problem is the magnetic containment. To get those magnetic fields to contain it and to get something that can sustain the energy, they need extraordinarily large magnetic fields that have a gradient that is phenomenal. It goes over like 6 orders of magnitude and a couple of inches. Stuff like this, and there's a guy over in physics that's doing that. I'm trying to think of his name, Dr. Thomas. Anybody have him ever? Do you know? He's doing that work. He reminds me of Neil deGrasse Tyson, if you know who that is. He's a great guy, very bright. But that kind of stuff is done by magnetic fields. And people that are very good with magnetic engineering, I mean, creating these kind of fields, they're worth a lot, especially probably overseas, because that stuff is used for a whole lot of other things. I don't know if they're ever going to get to the break-like even point. They've been working on it since I was in college. And it's the energy of the future. Here's what the deal is. Look at the sun. The sun's hot. Sun's very hot. It's been hot for a long time. It's going to be hot for a lot longer. All right, what's going on in the sun? Hydrogen is fused to helium, right? Liberates an incredible amount of energy. Follow me on this? Now, they're trying to do that on Earth, but in order to do that, you have to have a certain amount of pressure and temperature to create the reaction. Not only that, you got to be able to get hydrogen, ionized hydrogen, into this magnetic bottle without causing that field to rip apart and stuff like this, which is another problem. But all these problems they're trying to solve them. They're trying to solve them forever. I think they just want to keep getting money from the government. They've got stuff close, from what I've been told, where that can liberate enough heat to, boil water, put it through the actual cooling system and have it turn turbines before it does, and get energy out of it. But the amount of energy you need to sustain it, just the magnetic fields and everything like that, is greater than the energy out at this point in time. But they're working on it. I don't know if they'll ever get there, because they've been working on it longer than I can. Longer than I've been. No, that's not. They've been working on it probably 40 years. I'm older, but not older. So that's just something you should know. And now I'll tell you the story about the Bennett pinch. You see how all that stuff's being contained within there? Well, when Lloyd Riggs and I were up in Dogden, Virginia in 1987, we got a chance to visit a high-intensity physics laboratory that the actual Navy used. And this was in New Jersey. And what they were trying to do is create very high-intensity X-rays. And the way they do it is they charge these capacitor banks. It's called a Marks bank. And this is an extreme thing. They're talking about tens of millions to probably hundreds of millions of volts on these capacitors with a lot of charge. And they're going to discharge these things. And the way they discharge them is these electrons are literally going to hit a plate, and the plate is an X-ray, a thing that creates X-rays. I don't know the actual physics on how this works, but creates X-rays, and these high-intensity X-rays are then used for experiments. And I'm not sure everything they're doing. I don't know if it was a weapon or not. I just know I was there and I saw it. Well, they had all these charged capacitors. Now, when you get right here on Earth, does anybody know what the breakdown strength is of air? How much volts per meter would take the electric field strength in order to get an arc? Any idea? Just ask.
Air?
Huh? Yeah, air.
It's like 10 to the 6th, right? Or something.
3 million volts. It's about 3 million volts per meter. All right. All right. So if you do the math on this, no matter how you crack it, that's a lot of voltage. So even if you had a million volts on an actual capacitor, it's not per meter usually. I mean, you still don't have that in your mind's eye. You don't have the plates separated by a distance that would allow discharge. But here's the thing. Anytime you get a small piece of metal, a thin thing like just a strand or a pin, you get the field enhanced at the point, and that comes later, but you get field enhancement there. The field goes way up on the tip around there. So if you have any kind of a filament sticking out from one of those capacitor plates, then you can get an electric field that could easily break down the atmospheric thing. And here's the thing, as soon as you start a breakdown, think of lightning, because I did my doctoral work with lightning. As soon as it starts, it's almost always self-sustaining if there's enough charge there. This is called a step leader. As the ionization starts, it starts breaking down in front of that, and it's like one of these things, it's a runaway train if there's enough energy, and it'll just arc over to wherever the negative charge is. So it starts at the positive. And then as soon as it's done, it's like a short, and then the current just goes nuts. Lightning always has a step leader, a very faint, small, low current, or low amount of current, and as soon as that step leader connects from the top of the cloud, or from the cloud's charge center to the Earth, then that large flash comes, and that's the flashover. And it's immense. But anyway, without getting into lightning physics too much, when we were up there, they had these things charged, and somebody didn't do their proper diligence in making sure everything was trimmed down and there was some kind of a coating put on the actual leads and stuff like that, so you couldn't get this. And while these guys were working, nobody was down there. One of these, the capacitor bank was charged, and it discharged through the air and through a large rail about that thick of solid steel. And it was like, think about how loud lightning is. Well, now you're inside something Probably even a lot more current, a lot more energy was released in a lightning stroke. So these guys are shocked and, you know, trembling. They go in there to look at the damage. And the railing, this is one of the things that was damaged, was cut up into segments exactly the same length. And it was because it was called a magnetic shear. It's the Bennett pinch. When they get that field that's super intense like that, it cuts it, and there's a strange instability. It's called a Bennett instability, where they get sausage links literally created in a plasma. Well, literally the metal became the plasma. It was created, and it chopped it into, and I mean perfect sections that were like a high mill saw just cut those things. And that to me was very, very telling. That gave me a lot more respect for high intensity currents and lightning and stuff like that. Now lightning, when it hits, sometimes does stuff like that. If you've ever taken a look at wiring that was directly struck, you can see things like that. Not exactly like that, but similar. So that's sort of a story to give you some perspective. One other thing I'm going to do also on this today is talk about magnetic forces related to currents in parallel and currents that are in opposite directions. But first I have to say that if you have a B field, say the B field's going into the board, and assume it's uniform everywhere. Well, if I have a little chunk of current, I here, of length dl, that the magnetic force on this is equal to I dl crossed into B. That's important. So if you look at this, if B's into the board I dl cross B would be a magnetic force, and it would be upward. Follow me on that? Now, the reason that's important, you know that, is magnetic forces occur, whether we like them or not, with all sorts of wiring. And I'm going to start with a classic problem. I'm going to say, what if I have two wires? I have a current I here, same current I here, and they're at a distance d apart. And let's assume these are infinite wires, infinitely long. And I want to know how much force per meter is on these. So I'm looking for the force, but it's per meter, the magnetic force per meter. So how would you do that? Well, you're going to take one wire as the source of the magnetic field. So I'm going to use this as the source of the magnetic field. And I'm going to calculate the magnetic field from this wire at this point. So what I'm going to get is the B field right here. So what would that B field be? Well, we know the H field would be I over 2 pi rho in the A phi direction, or into the board. Do you agree with me? But I wanted the B field. What do I have to do? Multiply it by mu. Actually, mu naught. And here, I didn't talk about this much, but mu is the permeability. And it's permeability of free space. And mu naught is actually 4 pi times 10 to the minus 7, and that's henries per meter. That's the unit of mu, henries per meter. Remember, permittivity was farads per meter? This is henries per meter. And then they have something called mu relative also that talks about a material's ability to store magnetic energy. You remember epsilon relative had to do with the material's ability to store electric energy? The larger epsilon relative is, the more energy could be stored per unit volume for a given voltage across the plates. And with mu relative, it's how much more magnetic energy you can store relative to free space. Mu relative is typically from 1 to about maybe 1,000 typically. There are exotic materials where it gets up to 50,000, but it's like epsilon relative. It's not that much bigger. It's not 5 orders of magnitude bigger than 1, but it's somewhere between 1 and 1,000. For instance, any kind of thing used for iron cores for our transformers is about 1,000. It's laminated steel, it's about 1,000. If you have anything that's typical dielectrics, their mu relative is 1, so it's for all intents and purposes, it has no ability to store magnetic energy. This eraser is a good example. Something has no ability to store magnetic energy, more than free space would, but if you took a bar of iron, that has a lot of potential to store more because the mu relative of the iron is much higher. Anyway, so that's the magnetic field here. it's going into the board. Why don't we do it this way? Let me call this X, this Y, and this Z, and I'll just make this field in the A minus AX direction. All right? So it's in there. Now, next thing we take a look at is the force on this. So if the B field's going into the board right here, right? What direction is the force? And the current's going this way. This is my IDL, right? It's crossed into B to get the force, and that would be the differential force. So which way is the differential force? I got IDL crossed into B. Isn't it this way? You all see that, class? Sure. The force, the magnetic force, is going to be in this direction. And the magnitude of the magnetic force, or the value, would be simply I, magnitude of I times magnitude of B, right? And then it's going to be times dz, that's the dz direction, and it would be in the minus y direction. Y'all follow me on that? So if I go ahead and put in the equation, I could say the magnetic force on that wire per meter would be equal to I times B. Well, B is equal to mu 0 I over 2 pi rho, where the distance in this case is just d. All right, when I do the cross product, I get, well, I'm going to have dz here, and then I'm going to have minus ay direction. Now you'll notice the force is pulling this way. If you do this, yes?
It would be negative for the B.
Well, I've got the negative sign here.
Oh, okay.
Pull it up. So I'm saying that the force is in the negative ay direction. The force is in this direction. This is important. Also, I might say that the force on this wire is proven to be in this direction as well. And what you see is they're attracting, right? So then I can say that the force per meter, really the force per meter, if I just integrate dz from 0 to 1, I get a force per meter of mu 0 I squared over 2 pi b in the minus ay direction. Now, I'm going to tell you something. That's the force, right? Remember, mu 0 is, that's 4 pi times 10 to the minus 7th. So you would need an I value of 10 to the, of 10 to the 4th to get something appreciable up here. All right? Well, it depends on the actual separation distance, but here's my story on this one that you're going to like. I had a professor who worked at Los Alamos National Lab, he was a doctor, his name was Les Hale. And during the first nuclear weapons testing that were out there, this is literally the first A-bomb that was blown up. I mean, they did a lot of tests out there with nuclear weapons. They observed something interesting. But first, when a weapon goes off, a nuclear weapon, what happens is there's things called Compton electrons that are scattered to the far winds of the Earth. And these Compton electrons want to get back to the positive parent charge. So when they're blown away and they want to get back, they come through the path of least resistance. And metal is the least resistance material. Now out west, there are railroad tracks. This is a story I was told. I've never seen this in print, but I've got this from reliable sources, a couple of sources. So there, you remember in the 1800s, like 1850, 1860, the gold rush and stuff, they had railroad tracks were going across the US from like New York to San Francisco and stuff like that. Well, they went through this area, and a lot of it's buried because of, you know, sandstorms and all that crap. It's a desert out there, really. And when they did one of the aftermath digs to look at what the effects of the nuclear weapons were, they found that there were portions of a railroad track that had been buried where the two rails were pulled off the ties and fused together. Now, the amount of force to do that is extreme. And the currents, I don't know if there are millions of amps or tens of millions of amps to do this, but if I thought about that, and I thought, that's kind of terrifying because I don't know who did the assessment of Nagasaki and Hiroshima, but there were lots of people that went in and looked at the aftermath of nuclear weapons, and they found all sorts of weird things like this, that literally any pieces of metal that are parallel to each other with any length, they're basically, the forces on them are immense if the current wants to go through them. Like, if you have a bomb going off here, all the current's gonna be radial coming back and forth, right? If you have railroad tracks that are perpendicular, probably nothing happens. But if you have them like this, then they're gonna get a cajillion tons of current and they will probably pull together. I was amazed when I heard that. But anyway, I'm throwing that out there to let you know that's one of the things. When I see this, I think of that because that was the basic principle of work. All right, let me get you your quiz. And so separate yourselves with at least one empty desk. And close those notes.